Imagine something dies, and in that death it becomes more precise than almost anything alive. A star collapses. Its core is crushed into an object so dense that a teaspoon of it would weigh more than a mountain. And then, against every intuition you have about destruction and chaos, this dead remnant begins to spin, sending a beam of radiation sweeping through space with a regularity so exact that when astronomers first detected it, they seriously considered whether it might be a signal from an alien civilization. They weren't being dramatic. Nothing natural had any right to be that precise. And yet it was natural. A dead star, keeping time better than anything humans had ever built at the time of its discovery. Tonight, we're going to understand why. How stellar death can create one of the most astonishingly stable clocks the universe has ever produced. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. In 1967, at a radio astronomy observatory just outside Cambridge, England, a 24-year-old graduate student named Jocelyn Bell Burnell was doing something unglamorous. She was analysing paper. Literally hundreds of feet of chart paper, covered in squiggly ink traces, recorded by a radio telescope she had spent 2 years helping to build with her own hands. The telescope was not elegant. It was a field full of wooden posts and wire stretching across nearly 5 acres of English countryside, looking more like a sheep fence than a tool for exploring the cosmos. Designed by her supervisor, Anthony Hewish, to study how distant radio sources twinkle as their signals pass through the solar wind, it produced mountains of data. Bell Burnell's job was to comb through those recordings for anything interesting. She became very good at recognizing different kinds of signals. She could tell the difference between human-made radio interference and genuine astronomical sources by how they looked on the chart paper. Interference had a certain look to it, a certain character. Real signals from space had a different character. And then, one day, she noticed something that fit neither category. It was a small patch of what she later described as scruff, a bit of signal that didn't look like interference and didn't look like any known type of astronomical source. It was unusual enough to catch her eye, but not dramatic. Just a 1/4 inch of odd markings on a chart that stretched hundreds of feet. Most people would have ignored it. Bell Burnell didn't. She flagged it and kept watching. Over the following weeks, the signal appeared again and again, always from the same part of the sky. It came and went, which was strange. And when she finally managed to record it with faster chart speed, she saw something that made no sense. The signal was pulsing. It was a series of sharp, evenly spaced radio pulses, arriving with a period of 1.337 seconds. Not roughly 1.337 seconds. Not approximately. Exactly 1.337 seconds, repeating with a regularity that was almost mechanical. The pulses arrived like clockwork, steady and precise, one after another after another. This was deeply strange. Nothing in astronomy produced signals like this. Stars flicker and flare. Galaxies emit broad washes of radiation. Quasars vary over weeks or months. Nothing sent out precisely timed radio blips every 1.337 seconds. The precision was unsettling. It was too regular, too exact. Natural phenomena are messy. They're variable. They don't repeat with the accuracy of a metronome. The only things that produce signals this precise are machines. And so, half jokingly at first, and then with increasing seriousness, the team at Cambridge began to wonder whether they had detected a signal from an extraterrestrial civilization. They called the source LGM-1, Little Green Men 1. The name was partly humorous, but it reflected a genuine uncertainty. What natural process could possibly produce a signal this regular? Bell Burnell and Hewish discussed the possibilities and struggled to find a satisfying explanation. They checked whether the signal might originate within the solar system, reflected off a planet, or generated by human technology. It wasn't. The source tracked with the stars, rising and setting with sidereal time rather than solar time, meaning it was far beyond the solar system. They checked whether it might be an artifact of the telescope, some resonance in the wires or vibration in the equipment. It wasn't that either. The signal was real, coming from a definite position on the sky. For several weeks, the possibility of extraterrestrial intelligence hung in the air. It was exciting and terrifying in equal measure. Belle Burnell later recalled feeling annoyed at the prospect. She was trying to finish her doctoral thesis, and the idea that aliens might be trying to communicate with Earth was an inconvenient complication. But the scientific question remained. What was making this signal? Then Belle Burnell found another one, a second pulsing source in a completely different part of the sky with a different period, and then a third, and then a fourth. Each one pulsed with its own rhythm, but each was remarkably regular. The discovery of multiple sources was actually a relief, because it made the alien hypothesis far less likely. It would be one thing if a single advanced civilization were broadcasting a signal from one location, but 4 separate civilizations in 4 different parts of the galaxy, all independently deciding to send precisely timed radio signals in Earth's direction. That strained credulity. Whatever was producing these signals, it was a natural phenomenon. Something in the universe was creating radio pulses with a regularity that rivaled the most precise human instruments. And whatever it wasn't rare. There were apparently many of them scattered across the sky. The announcement came in February of 1968, published in the journal Nature. The sources were designated with the catalogue prefix CP for Cambridge Pulsar. The first one, the original bit of scruff that Belle Burnell had noticed, became CP 1919. The scientific community was stunned. Nothing like this had ever been observed. The question immediately became not whether these signals were real, but what was producing them. Something out there was pulsing with extraordinary precision. What kind of object could do that? The first explanations people considered were the obvious ones. Could it be a star that was vibrating, physically expanding and contracting in a rhythmic way? Stars do this. There's an entire category of stars called variable stars that pulsate, swelling and shrinking as energy moves through their interiors. Some of them are remarkably regular. But variable stars pulsate over periods of hours, days, or even weeks. Not once every second or so. The physics of stellar pulsation simply doesn't allow a star to vibrate that quickly. The period of pulsation depends on the star's density. The denser the star, the faster it can pulsate. An ordinary star like our Sun has far too low a density to pulsate once per second. Even a white dwarf, one of the densest stellar objects known at the time, couldn't pulsate that fast. The periods didn't match. Stellar pulsation was ruled out. Could it be a binary star system? 2 stars orbiting each other so quickly that they produced a periodic signal as one passed in front of the other. Binary systems do produce periodic signals, but for 2 stars to orbit each other every 1.337 seconds, they would need to be impossibly close together. You can calculate the orbital separation required using Kepler's laws, and the answer is that the 2 objects would need to be practically touching or even overlapping. No binary system of ordinary stars could have an orbital period this short. The stars would merge or tear each other apart. Binary orbiting was ruled out. Could it be a white dwarf rotating? White dwarfs are dense, compact stellar remnants, roughly the size of Earth, but containing about the mass of the Sun. They're left behind when a star, like our Sun, exhausts its fuel and sheds its outer layers. A rotating white dwarf could, in principle, produce a periodic signal if it had a bright spot that swept past our line of sight with each rotation, like a lighthouse. But could a white dwarf rotate once every second or faster? The answer is no. If you spin a white dwarf that fast, it tears itself apart. The centrifugal force at the equator exceeds the gravitational force holding it together. White dwarfs are dense, but they're not dense enough to withstand rotation periods of a second or less. Rotating white dwarfs were ruled out. And so, by a process of elimination, astronomers arrived at the only remaining possibility. The pulsing sources had to be neutron stars. Rotating neutron stars. The term pulsar, a contraction of pulsating star, was coined shortly after, and it stuck. But the name is slightly misleading, because the star isn't actually pulsating. It isn't expanding and contracting, it's rotating. The pulses are produced because the neutron star spins, sweeping a beam of radiation around like a lighthouse sweeps its beam across the ocean. Every time the beam points toward Earth, we detect a pulse. The incredible regularity of the pulses reflects the incredible regularity of the rotation. The neutron star is spinning at a nearly constant rate, and each rotation sends one flash of radio waves in our direction. The pulse period is simply the rotation period. The star spins once, you get one pulse. It spins again, you get another. 1.337 seconds between pulses means the star is rotating once every 1.337 seconds. This explanation drew on work by Franco Pacini, who had predicted in 1967 that a rotating, magnetized neutron star would radiate energy, and Thomas Gold, who in 1968 specifically proposed that pulsars were rotating neutron stars sweeping beams of radiation through space. Gold, in particular, laid out the case clearly. The pulsing signal was not coming from a star that was vibrating, orbiting, or flickering. It was coming from a neutron star that was spinning, with a beam of radiation anchored to its magnetic field. The beam swept through space as the star rotated, and observers along the beam's path would see a regular pulse. Observers outside the beam's path would see nothing at all. The pulsar wouldn't be detectable from every direction, only from certain vantage points, those that happen to lie in the path of the rotating beam. But to understand why this explanation works, you need to understand what a neutron star actually is. And this is where the story becomes extraordinary. A neutron star is what remains after a massive star dies. Not a star like our Sun, which is too small to produce a neutron star. The Sun will eventually swell into a red giant and then shed its outer layers, leaving behind a white dwarf. A neutron star requires a much more massive progenitor, a star at least 8 to 10 times the mass of the Sun. These massive stars live fast and die violently. They burn through their nuclear fuel in a few million years, a blink of an eye compared to the Sun's 10 billion year lifespan. And when they run out of fuel, they don't fade quietly. They explode. Here's what happens. Throughout its life, a massive star is engaged in a constant battle between two forces. Gravity pulls everything inward, trying to collapse the star into a single point. Nuclear fusion in the core pushes outward, generating enough energy and pressure to resist gravity's crush. For millions of years, these two forces balance each other. The star holds its shape. It shines steadily. It seems stable. But fusion requires fuel, and the fuel is finite. The star begins by fusing hydrogen into helium in its core. When the hydrogen runs out, the core contracts and heats up until it's hot enough to fuse helium into carbon and oxygen. When the helium runs out, the core contracts further and begins fusing carbon into heavier elements, then neon, then oxygen, then silicon. Each successive fuel burns faster than the last. Hydrogen fusion lasts millions of years. Silicon fusion, the final stage, lasts about a single day. The star is running out of options, and it's running out fast. The final product of silicon fusion is iron, and iron is a dead end. Every element lighter than iron releases energy when fused into heavier elements. That released energy is what powers the star and holds it up against gravity. But iron is different. Fusing iron doesn't release energy. It requires energy. It costs more than it gives. When the core fills with iron, fusion stops. The energy source that has been holding the star up for millions of years simply switches off. And in that moment, gravity wins. What happens next takes less than a second. The iron core, which is roughly the size of Earth at this point, about 8,000 miles across, collapses under its own weight. There is nothing to stop it. No outward pressure, no energy source, nothing. The collapse happens at a significant fraction of the speed of light. Material falls inward at speeds reaching 70,000 kilometers per second. The collapse is not a smooth, gentle compression. It's a catastrophic freefall. The outer layers of the iron core don't even know the inner layers have started falling until the collapse is already well underway. Information about the collapse travels at the speed of sound in the core material, but the material itself is falling faster than sound can propagate through it. The core is collapsing supersonically. The outer parts of the core are still sitting there, supported by the pressure beneath them, when that support suddenly vanishes. They plunge inward, chasing the inner core, accelerating as they fall. The inner core reaches nuclear density first. In a fraction of a second, the material at the very center of the star is compressed to the point where neutrons are packed as tightly as physics allows. And at that moment, the collapse stops. Not gradually, not gently. It stops abruptly. Because nuclear matter is extraordinarily incompressible. It's like slamming into a wall. The inner core, falling inward at a significant fraction of the speed of light, suddenly hits a floor of nuclear density matter that refuses to compress any further. The infalling material doesn't just stop, it bounces. The inner core overshoots its equilibrium density slightly, then springs back, like a rubber ball that has been squeezed and released. This bounce sends a shockwave outward through the still infalling outer core. The shockwave is immensely powerful, but initially it's not powerful enough. As it pushes outward through the infalling material, it loses energy. It has to work against gravity. It has to push against material that is still falling inward at tens of thousands of kilometers per second. Within milliseconds, the shockwave stalls. It stops expanding. For a brief, critical moment, the explosion hangs in the balance. The shockwave is stuck, and if nothing revives it, the entire star will simply collapse into a black hole. What revives it is neutrinos. The newly formed neutron star at the center is radiating neutrinos at an almost inconceivable rate. In the first few seconds, the neutron star emits more energy in neutrinos than the Sun will produce in its entire lifetime. Neutrinos barely interact with matter under normal conditions. They pass through the Earth as if it weren't there. But at the densities present in the collapsing core, even neutrinos are partially trapped. A small fraction of the outpouring neutrino energy is absorbed by the material just behind the stalled shockwave. This deposited energy reheats the material, revives the shockwave, and drives it outward through the rest of the star. The explosion is on. In less than a second, the core goes from being roughly the size of Earth to being roughly the size of a city. A sphere about 12 miles across. The collapse is halted not by fusion, not by heat, not by any familiar kind of pressure, but by the fundamental nature of matter itself. During the collapse, conditions become so extreme that atoms are crushed out of existence. The electrons that normally orbit atomic nuclei are forced inward, merging with protons to form neutrons. This process releases a flood of ghostly particles called neutrinos, which carry away enormous amounts of energy. The entire core is converted into a ball of neutrons packed so tightly that they touch. Atomic structure is gone. There are no atoms anymore, no electrons orbiting nuclei. no empty space within atoms. Just neutrons, pressed against each other at densities that almost defy description. The density of a neutron star is approximately 400 trillion grams per cubic centimetre. Let me try to make that real for you. Take a sugar cube. A normal sugar cube, the kind you might drop into a cup of coffee, about 1 cubic centimetre. Now imagine that sugar cube weighing 400 trillion grams. That's roughly 400 million tons, a single sugar cube's worth of neutron star material, placed on Earth's surface, would weigh about as much as every human being on the planet combined. All 8 billion of us packed into a cube you could hold between your thumb and forefinger. And the entire neutron star is made of this material. A sphere about 20 kilometers across, 12 miles or so, containing somewhere between 1.4 and 2 times the mass of the Sun. All the material that once filled a stellar core the size of Earth has been compressed into something you could fit inside the boundaries of a mid-sized city. This is not just dense, this is a fundamentally different state of matter. On Earth, matter is mostly empty space. An atom is overwhelmingly empty. If you enlarged an atom to the size of a football stadium, the nucleus at the center would be about the size of a marble. Everything between the nucleus and the electrons is nothing. Empty vacuum. Solid objects feel solid only because electromagnetic forces between atoms resist compression. But inside a neutron star, those electromagnetic forces have been overwhelmed. The empty space within atoms has been crushed out. Matter has been compressed to nuclear density, the density of an atomic nucleus, but on a scale of kilometers rather than femtometers. A neutron star is essentially one giant atomic nucleus, 20 kilometers across, held together by gravity. The collapse of the core is only part of the story. When the infalling material hits the newly formed neutron star and bounces, it sends a shockwave back outward through the rest of the star. This shockwave, energized by the flood of neutrinos pouring out of the core, tears the star apart from the inside. The outer layers of the star, tens of solar masses worth of gas and plasma, are blown outward into space at thousands of kilometers per second. This is a supernova, one of the most violent events in the universe. For a few weeks, a single exploding star can outshine an entire galaxy containing hundreds of billions of stars. The energy released in a supernova is almost incomprehensible. In a few seconds, a collapsing star emits more energy in neutrinos alone than the Sun will produce in its entire 10 billion year lifetime. When the explosion fades, when the debris expands and cools and becomes a glowing nebula, like the Crab Nebula visible in the constellation Taurus, what remains at the center is the neutron star. Small, dense, and incredibly hot. Its surface temperature is initially around 1 trillion degrees. It glows with radiation across the electromagnetic spectrum, and critically for our story, it is spinning. Its surface temperature is initially tens of billions of degrees, hot enough that it radiates across the electromagnetic spectrum, from radio waves to gamma rays. The idea that neutron stars might exist was actually proposed decades before pulsars were discovered. In 1934, 2 astronomers named Walter Baade and Fritz Zwicky suggested that when massive stars explode as supernovae, they might leave behind incredibly dense remnants composed primarily of neutrons. This was only 2 years after the neutron itself had been discovered. It was a remarkable theoretical prediction, but for over 30 years, nobody knew how to observe a neutron star. They were too small and too faint to see directly with the telescopes available at the time. A neutron star is only about 20 kilometers across. At the distance of even the nearest stars, that's far too tiny to resolve as anything other than a point of light, if you could see it at all. The discovery of pulsars in 1967 finally provided the observational evidence. Neutron stars weren't just theoretical, they were real, they were out there, and they were spinning, sweeping beams of radiation through space like cosmic lighthouses. The scruff that Jocelyn Bell Burnell noticed on her chart paper turned out to be the first direct evidence for one of the most extraordinary objects in the universe. A dead star's core, crushed to nuclear density, spinning in the darkness, keeping time with a precision that astonished everyone who studied it. There's a deep irony in this. The neutron star is a product of destruction. It was born in an explosion so violent that it briefly outshone hundreds of billions of stars. Everything about its creation is chaotic and extreme. Temperatures of trillions of degrees, pressures beyond imagination, matter crushed into states that don't exist anywhere else in the observable universe. And yet, from all that violence and chaos, emerges an object of extraordinary order, a spinning remnant so regular in its behavior that it can serve as a clock. Not a rough clock, not an approximate timekeeper, a precision instrument, steady enough that its pulses can be predicted to within microseconds over years of observation. How? How does total destruction produce such extraordinary precision? That question is at the heart of everything that follows. The answer lies not in some special property that neutron stars happen to have by accident, but in the fundamental physics of what happens when a massive object collapses. When something that large contracts to something that small, physics demands that certain quantities be conserved, and one of those quantities, angular momentum, is the key to everything. It's the reason a dead star becomes a clock. It's the reason that clock keeps such extraordinary time. And understanding it will reveal why a pulsar can rival the most precise instruments humanity has ever constructed. The neutron star sitting at the center of a supernova remnant is not merely a curiosity. It's not just one more exotic object on a long list of exotic objects that astronomers have catalogued over the centuries. It is a fundamentally different kind of thing. It is matter compressed beyond any state we can reproduce on Earth, spinning in the vacuum of space, emitting radiation along narrow beams that sweep through the cosmos with metronomic regularity. And the precision of those sweeping beams, the steadiness of that rotation, turns out to be one of the most remarkable phenomena in all of astrophysics. Not because someone designed it to be precise, but because the physics of collapsing matter, of conservation laws applied at stellar scales, of extraordinary density and rigidity in a near-perfect vacuum, makes precision inevitable. That inevitability is what we need to understand. It's not enough to know that pulsars exist and that they pulse regularly. The real question is why. Why does the collapse of a star produce something so stable? Why doesn't the neutron star wobble or slow down quickly or behave erratically the way so many other astrophysical objects do? What is it about this particular kind of object, at this particular scale of density and compactness, that produces the steadiest natural rotation the universe has to offer? The answer starts with a principle so fundamental that it governs everything from spinning figure skaters to collapsing galaxies. And it will take us into the physics of why the death of a star doesn't just create a remnant, it creates a clock. To understand why a collapsing star becomes a clock, you need to understand one of the most fundamental principles in all of physics. It's called conservation of angular momentum. The name sounds technical, but the idea behind it is something you've seen with your own eyes, probably hundreds of times, without ever thinking about the physics involved. Watch a figure skater perform a spin. She starts with her arms extended wide, turning slowly on the ice. Then she pulls her arms in close to her body, and the moment she does, she spins faster, dramatically faster. She hasn't pushed off anything. She hasn't applied any new force. She hasn't activated some hidden motor. She simply pulled her arms inward, and physics did the rest. She went from a graceful, slow rotation to a blinding whirl in a fraction of a second. This is angular momentum conservation in action. And it's the same principle that turns a dying star into a precision timepiece. Angular momentum is a measure of how much rotational motion an object has. It depends on two things. First, how fast the object is spinning, and second, how the object's mass is distributed relative to the axis of rotation. If the mass is spread far from the axis, Like a skater's extended arms, the object has a lot of what physicists call moment of inertia. It resists changes in rotation. It's rotationally sluggish. If the mass is pulled close to the axis, the moment of inertia drops. The object becomes rotationally nimble. Here's the critical part. In the absence of an external force or torque acting on the system, angular momentum cannot change. It is conserved. It's one of the deepest laws of nature, rooted in the symmetry of space itself. The universe doesn't care which direction you're facing. Physics works the same whether you're pointed north, south, east, or west. And from that simple symmetry, mathematically, inevitably, comes the law that angular momentum is conserved. So when the skater pulls her arms in, her moment of inertia decreases. But angular momentum has to stay the same. The only way that equation balances is if her rotation rate increases. She spins faster to compensate for the decrease in how far her mass is spread from her axis. This isn't a choice. It's a mathematical necessity. Angular momentum equals the moment of inertia multiplied by the rotation rate. If one goes down and the product must stay the same, the other must go up. Now take that principle and apply it to a dying star. Before it collapses, the iron core of a massive star is roughly the size of Earth, about 12,000 kilometers across, and it's rotating. Not fast by everyday standards. The core might be completing one rotation every few seconds, or perhaps every few tens of seconds. Stars rotate. The Sun rotates once roughly every 25 days at its equator. More massive stars often rotate faster. And the cores of massive stars, deep inside where the iron is accumulating, rotate at their own rate, sometimes faster than the surface. The exact rotation speed depends on the star's history, its mass, how angular momentum was transported through its interior over millions of years. But the core is rotating. That's the key point. It has angular momentum. Then the core collapses. In less than a second, it goes from being 12,000 kilometers across to being about 20 kilometers across. Think about what that means in terms of the figure skater analogy. The skater pulls her arms from maybe a meter out to a few centimeters from her body. That's a reduction in radius of maybe a factor of 10 or 20. The collapsing stellar core goes from a radius of about 6,000 kilometers to a radius of about 10 kilometers. That's a reduction by a factor of roughly 600. Angular momentum is conserved. The moment of inertia of a spinning sphere depends on the square of its radius. So when the radius decreases by a factor of 600, the moment of inertia decreases by a factor of 600 squared, which is 360,000. And if the moment of inertia drops by a factor of 360,000, while angular momentum stays constant, the rotation rate must increase by the same factor. A core that was rotating once every 30 seconds would suddenly be spinning about 12,000 times per second. That's far faster than any pulsar ever observed. And in practice, the numbers come out lower, because some angular momentum is carried away by the material ejected in the supernova explosion. Now in practice, the numbers don't always work out quite that dramatically. Some angular momentum is carried away by the material ejected in the supernova explosion. Some is carried off by the neutrinos that flood out during the collapse. The coupling between different layers of the star is complicated, but the basic result holds. A slowly rotating stellar core becomes a rapidly spinning neutron star. Rotation periods that were measured in seconds or minutes become rotation periods measured in milliseconds. The collapse takes something that was turning lazily and compresses it into something that whirls at extraordinary speed. This is not some exotic or unusual piece of physics. This is the same principle that governs everything from the spin of a top to the rotation of hurricanes. When material contracts toward a central axis and angular momentum is conserved, the rotation rate increases. The only unusual thing about a neutron star is the scale. The compression is so extreme, the radius changes by such an enormous factor, that the resulting spin rate is orders of magnitude faster than the original. A star that rotated once a day becomes a neutron star that rotates many times per second. The physics is ordinary. The scale is extraordinary. The Crab Pulsar, sitting at the center of the Crab Nebula, is one of the youngest known pulsars. It was created in a supernova explosion observed by Chinese astronomers in the year 1054. That supernova was so bright it was visible during the daytime for 23 days. Nearly 1,000 years later, the neutron star left behind is still spinning about 30 times per second. It has slowed down over the centuries, gradually losing rotational energy, but it's still spinning incredibly fast. 30 rotations per second means the surface at the equator of this object, which is roughly 10 kilometers in radius, is moving at roughly 1,900 kilometers per second. That's more than 0.5% of the speed of light. The surface of a neutron star, a solid surface made of material denser than an atomic nucleus, is moving at a significant fraction of the speed of light. This is not a gentle rotation. This is a violent, screaming spin, driven by the compression of an entire stellar core into something smaller than a city. But speed alone doesn't make a clock. Plenty of things spin fast without being precise. A spinning top wobbles. A spinning wheel in a factory vibrates. A tornado rotates rapidly, but its rotation is chaotic, variable, unpredictable. What makes a pulsar exceptional isn't just that it spins fast. It's that it spins with almost unbelievable stability. The rotation rate barely changes. Year after year, decade after decade, the pulsar ticks away with a regularity that puts most human-made timekeepers to shame. And this stability, this constancy, is just as important to the pulsar's nature as a clock as the rapid spin itself. So why is the spin so stable? Why doesn't the neutron star slow down quickly, or wobble, or fluctuate erratically? The answer comes down to three things: density, rigidity, and the near total absence of anything to slow it down. Start with density. A neutron star is the densest object that can exist without becoming a black hole. Its matter is compressed to the point where neutrons are packed shoulder to shoulder, occupying the minimum space that the laws of quantum mechanics allow. There is no empty space left to squeeze out. The material is incompressible in any practical sense. This extreme density means the neutron star has an enormous amount of rotational energy stored in a very small, very compact package. When something this dense spins, it has tremendous rotational inertia. It resists changes to its spin the way a massive flywheel resists being slowed down. A lightweight bicycle wheel can be stopped easily with your hand. A massive industrial flywheel made of solid steel takes enormous force to slow down. A neutron star is like a flywheel made of the densest material in existence, compressed into a sphere 20 kilometers across, spinning at a rate that would tear apart any material we know of on Earth. The amount of energy stored in its rotation is staggering. The rotational energy of a young pulsar like the Crab is on the order of 10 to the 42nd joules. For the fastest millisecond pulsars, spinning hundreds of times per second, that figure climbs to 10 to the 45th joules, comparable to the total energy output of the Sun over its entire 10 billion year lifetime, all stored in the spin of a single compact object. To significantly slow this rotation, you'd need to extract an enormous amount of energy. Small perturbations, small forces, simply don't matter. They're drowned out by the sheer rotational inertia of the system. Now consider rigidity. A neutron star is not a ball of gas or liquid, not at the surface anyway. The outer layer of a neutron star, called the crust, is a crystalline lattice of atomic nuclei embedded in a sea of electrons. This crust is extraordinarily rigid. The material is more than 1 billion times stiffer than steel. If you could somehow build a structure out of neutron star crust material, it would be essentially unbreakable by any force available in normal engineering. The rigidity matters because a rigid body rotates more cleanly than a fluid one. Think about the difference between spinning a raw egg and spinning a hard-boiled egg on a tabletop. The raw egg wobbles and slows down quickly because the liquid inside sloshes around, dissipating energy. The hard-boiled egg spins more smoothly and longer because it's solid all the way through. A neutron star is the ultimate hard-boiled egg. Its crust is crystalline and unimaginably stiff. Its interior, while it may have superfluid components, is locked into a state of matter so exotic that it doesn't behave like ordinary fluids. The whole object rotates as a nearly perfect rigid body, with almost no internal energy dissipation from sloshing or turbulence. But saying the neutron star is rigid doesn't capture the full picture. To truly understand why the spin is so stable, you need to understand what the interior of a neutron star actually looks like. Because it's not uniform. It has layers like an onion, and each layer is made of progressively stranger material as you move from the surface toward the center. The outermost layer is the crust. It begins at the surface, where the density is relatively low by neutron star standards, comparable to the density of iron on Earth's surface, though compressed under a gravitational field roughly 200 billion times stronger than Earth's. At this surface layer, matter is arranged in a crystalline lattice of iron nuclei, held rigidly in place by the immense pressure. This is a true solid, perhaps the stiffest solid in the universe. If you could somehow extract a piece of neutron star crust the size of a playing card, it would weigh hundreds of millions of tons and be essentially indestructible by any force available in a terrestrial laboratory. You could not bend it, break it, or scratch it with any tool that exists on Earth. As you move deeper into the crust, the density increases and the nuclei become more neutron-rich. The intense pressure forces electrons to merge with protons, converting them into neutrons, just as happened during the initial collapse. Nuclei become bloated with extra neutrons, taking on configurations that don't exist in any element found on Earth. These exotic nuclei are arranged in the same crystalline lattice, but they're swollen with neutrons that are barely held within the nuclear structure. At a certain depth, neutrons begin to drip out of the nuclei entirely, forming a free neutron gas that permeates the spaces between the lattice of nuclei. This region is called the neutron drip layer. It's a state of matter that exists nowhere else in the observable universe. A crystalline solid interpenetrated by a gas of free neutrons. Go deeper still, and you enter the outer core, where the crust gives way entirely. Here, matter is a uniform fluid of neutrons with a small admixture of protons and electrons. The density is now above nuclear density, several 100 trillion grams per cubic centimeter, and the physics governing this material is genuinely exotic. The neutrons in this region are thought to form a superfluid. Not a superfluid like the liquid helium you might have seen in a physics demonstration, cooled to near absolute zero and flowing without viscosity over the rim of its container. The temperatures inside a neutron star are millions of degrees. But the neutrons pair up through quantum mechanical interactions, forming what physicists call Cooper pairs, analogous to the electron pairing that produces superconductivity in metals. These paired neutrons flow without friction. They are a superfluid even at millions of degrees because the relevant energy scale is set not by temperature in the everyday sense, but by the nuclear binding energy, which is enormous. The protons in the outer core are also thought to pair up and become superconducting. A superconductor expels magnetic fields from its interior, or confines them to narrow channels called flux tubes. This means the magnetic field threading through the neutron star's core is not smoothly distributed. It's confined to an array of thin magnetic flux tubes, each carrying a quantum of magnetic flux, threading through the superconducting proton fluid like threads through fabric. This layered structure matters for the pulsar's stability in a specific and important way. The superfluid neutrons in the interior can, under certain conditions, rotate at a slightly different rate than the rigid crust. Superfluids don't rotate the way ordinary fluids do. Instead of spinning as a continuous mass, a superfluid rotates by forming an array of tiny quantum vortices, each one a microscopic tornado of circulating superfluid. The number and arrangement of these vortices determines the superfluid's effective rotation rate. If the crust slows down due to magnetic braking, the superfluid interior doesn't automatically slow down with it. The vortices have to migrate outward to reduce the superfluid's rotation rate, and they can become pinned, stuck to nuclei in the crust or to magnetic flux tubes in the core. When this happens, the superfluid maintains its faster rotation rate even as the crust slows down. A differential rotation builds up between the interior and the exterior. Occasionally, the stress becomes too great, and the pinned vortices suddenly unpin and migrate outward in an avalanche. When this happens, angular momentum is abruptly transferred from the faster spinning superfluid interior to the slower spinning crust. The crust speeds up slightly. This is a glitch, a sudden tiny increase in the pulsar's rotation rate. Glitches are small, typically changing the spin rate by less than 1 part in a billion. But they're detectable precisely because the normal rotation is so incredibly stable that even a change this small stands out against the smooth, predictable slowdown. The fact that glitches are so small tells you something important about how tightly coupled the crust and interior are under normal conditions. The vast majority of the time, the entire neutron star rotates as one body. The crust, the superfluid neutrons, the superconducting protons, all of them are locked together and spinning at essentially the same rate. The coupling mechanisms, the interactions between vortices and flux tubes and the crystal lattice, are strong enough to maintain near-perfect co-rotation almost all the time. Glitches are the exceptions, brief moments when the coupling temporarily fails and then reasserts itself. Between glitches, the neutron star is a unified rotator of extraordinary stability. Now consider the magnetic field itself and where it came from. The neutron star's magnetic field is inherited from the progenitor star, amplified enormously by the same collapse that amplified the rotation. Magnetic flux, like angular momentum, is approximately conserved during collapse. The total magnetic flux threading through the core stays roughly constant as the core shrinks. But flux equals field strength multiplied by area. When the core contracts from thousands of kilometers across to about 20 kilometers, the area decreases by a factor of hundreds of thousands. If the flux stays constant and the area drops by that factor, the field strength must increase by the same factor. A progenitor core with a magnetic field of thousands of Gauss, compressed by a factor of hundreds of thousands in radius squared, already produces a field of billions of Gauss through flux conservation alone. But the final field of a young pulsar, often reaching 1 trillion Gauss or more, likely requires additional amplification. During the violent convection that drives the supernova explosion, turbulent dynamo processes can wind and stretch the magnetic field, boosting it by additional orders of magnitude in the seconds surrounding the collapse. The compression provides the foundation, and the violence of the birth amplifies it further. This amplified field is then frozen into the highly conductive neutron star material. In the crust, the field is anchored to the rigid crystalline lattice. In the superconducting core, it's confined to the flux tube array. The field rotates with the star as a rigid structure, and it maintains its configuration over long timescales because the conductivity is so high that the field cannot easily diffuse or dissipate. The field decays, but slowly, over millions of years. On the timescales relevant for pulsar observations, decades to centuries, the field is effectively permanent and unchanging. This means the beam geometry is also effectively permanent and unchanging. The beam sweeps through space at the same angle, with the same width, rotation after rotation, year after year. The signal you receive is not just periodic, it's identically periodic. Each pulse is a near-perfect copy of the last, because neither the rotation nor the beam geometry changes measurably over human observational timescales. And then there's the vacuum. A neutron star is spinning in space. There is no air, no friction, no medium dragging against its surface. On Earth, every spinning object eventually slows down because of friction and air resistance. A bicycle wheel stops because air pushes against the spokes and bearing friction dissipates energy. A top falls over because air resistance and contact friction slow its spin until gyroscopic stability is lost. But in space, there is essentially nothing to push against a spinning neutron star. No atmosphere, no contact surface, no medium to create drag. The neutron star is a hyperdense, ultra-rigid sphere spinning in a vacuum, and there is almost nothing acting to change its rotation. I say almost nothing because pulsars do slow down, very, very gradually. The primary mechanism is magnetic dipole radiation. The neutron star has an enormously powerful magnetic field, typically about 1 trillion times stronger than Earth's magnetic field. This magnetic field rotates with the star, and a rotating magnetic field emits electromagnetic radiation. This radiation carries away energy, and that energy comes from the rotation. So the pulsar slowly loses rotational energy, and its spin gradually decreases. But the key word is slowly. The rate of slowdown is tiny. A typical pulsar might lose about 1/1,000,000th of a second from its period over the course of a year. Some pulsars are even more stable than that. The Crab pulsar, which is young and has a strong magnetic field, slows down relatively quickly by pulsar standards. It's losing about 38 nanoseconds per day from its period. That sounds like a lot, but remember, it's spinning 30 times per second. Losing 38 billionths of a second per day from a period of about 33 milliseconds is a fractional change so small it takes sensitive instruments to even detect it. And this gradual slowdown is itself remarkably smooth and predictable. Astronomers can measure the rate at which a pulsar is slowing down, and use that measurement to predict the arrival time of future pulses with extraordinary accuracy. The slowdown follows a simple mathematical relationship. It's not erratic, it's not random. The pulsar spins down steadily, like a top on a frictionless surface that is losing energy only through a single, well-understood mechanism. You can account for the slowdown, subtract it out, and what remains is a clock of astonishing precision. This combination of properties, the enormous rotational inertia, the extraordinary rigidity, the near-perfect vacuum, and the slow, predictable energy loss, is what makes a pulsar such a remarkable timekeeper. It's not one of these factors alone, it's all of them working together. Any one of them would contribute to stability. All of them together produce something that is almost supernaturally precise. Now, there's one more piece of the puzzle. Understanding why the pulsar spins fast and why that spin is stable explains why the rotation itself is regular. But pulsars aren't observed as steadily glowing objects. They're observed as pulsing sources, blinking on and off like a lighthouse. To understand the pulses, you need to understand the geometry of the beam. A neutron star has an extremely powerful magnetic field. In most neutron stars, this magnetic field has a dipole structure, meaning it has a north and south magnetic pole, similar in shape to a bar magnet. Charged particles near the neutron star, electrons and positrons, created in the intense electromagnetic environment around the star, are accelerated along the magnetic field lines near the poles. These accelerated particles emit radiation, particularly radio waves, in narrow beams concentrated above the magnetic poles. Here is the critical geometric detail. The magnetic axis of a neutron star is generally not aligned with its rotation axis. Think about Earth. Earth's geographic North Pole, the point around which the planet rotates, is not in exactly the same place as Earth's magnetic North Pole. They're offset by several degrees. The same is true for neutron stars, but often to a much greater degree. The magnetic poles can be substantially tilted relative to the spin axis. This misalignment is everything. If the magnetic axis were perfectly aligned with the spin axis, the beams of radiation would point in the same direction all the time. They'd trace out circles around the sky, but they wouldn't sweep past any given observer in a periodic way. There would be no pulses. The source would just appear as a constant emitter if you were in the beam's path, or invisible if you weren't. But because the magnetic axis is tilted, the beams don't point in a fixed direction. They're carried around by the star's rotation, sweeping through space like the beams of a lighthouse. Each time one of the beams swings past Earth's line of sight, radio telescopes detect a brief pulse of radiation. One rotation, one pulse. Imagine holding a flashlight at arm's length and tilting it away from vertical. Now spin around in place. The flashlight beam sweeps across the walls of the room, briefly illuminating each point as it passes. Anyone standing in the room would see a periodic flash every time you completed one rotation. That's what a pulsar does. Except the flashlight is a beam of radio waves generated by charged particles streaming along magnetic field lines above the neutron star's magnetic pole, and the room is interstellar space. This lighthouse model explains several key observational features. First, it explains why the pulse period equals the rotation period. Each rotation sweeps the beam past the observer once. Second, it explains why we don't see pulses from all neutron stars. If the beam never sweeps across Earth's line of sight, we simply never detect the pulsar. It's still there, still spinning, still emitting beams, but the beams are aimed in directions that miss us entirely. Astronomers estimate that for every pulsar we detect, there may be several more that are beaming in directions we'll never see from our particular vantage point in the galaxy. Third, the lighthouse model explains the shape of the pulse. As the beam sweeps past, we see the signal rise as the edge of the beam approaches, peak as it crosses our line of sight, and fall off as it moves away. The exact pulse profile, the shape of the signal over one rotation period, depends on the beam geometry, the tilt angle, and the structure of the emission region above the magnetic pole. Different pulsars have different pulse profiles, some with single sharp peaks, others with multiple peaks, depending on these geometric details. The beauty of this model is its simplicity. The pulse is not produced by some complicated oscillation or internal process within the star. It's produced by geometry, a spinning object with a tilted beam. The regularity of the pulse comes directly from the regularity of the spin. If the spin is stable, the pulses are stable. If the spin is predictable, the pulses are predictable. The pulsar is a clock, not because it has some internal ticking mechanism, but because its rotation is stable and its beam geometry is fixed. The rotation provides the timekeeping. The tilted magnetic field provides the signal. Together, they produce the most regular natural phenomenon astronomers have ever observed. There's something deeply satisfying about this. The pulsar doesn't need to be complicated to be precise. In fact, its precision comes from its simplicity. It's a dense sphere, spinning in a vacuum, with a tilted beam. That's it. There are no moving parts in the conventional sense. No gears, no springs, no oscillating crystals. Just rotation. Pure, steady rotation, governed by the conservation of angular momentum and sustained by the incredible density and rigidity of the neutron star. The pulsar is precise because the physics governing its behavior is simple, and because the conditions that could disrupt that simplicity, friction, drag, internal turbulence, are almost entirely absent. Compare this to the way we build clocks on Earth. A pendulum clock is affected by temperature, air resistance, vibrations, and humidity. A quartz clock is better, but quartz crystals drift with temperature and aging. Atomic clocks are better still, using the transition frequency of atoms, a fundamental constant of nature. But even atomic clocks need careful environmental control, shielding from magnetic fields, temperature regulation, and vacuum chambers. A pulsar achieves its stability through brute force, in a sense. It doesn't need careful environmental control because there's nothing in its environment to disturb it. It doesn't need shielding from magnetic fields because it is the magnetic field. It doesn't need a vacuum chamber because it exists in the best vacuum available, interstellar space. Its timekeeping is built into its physical structure, into the conservation laws that govern its spin, into the density that gives it rotational inertia, into the rigidity that prevents internal dissipation, into the vacuum that eliminates drag. The precision is not engineered, it's emergent. It arises inevitably from the physics of a collapsed stellar core. And this emergent precision was there from the very beginning. From the moment the core finished collapsing and the neutron star settled into its final state, it was already a clock. Nobody had to calibrate it. Nobody had to adjust it. Nobody had to set it. The collapse itself created the conditions for extraordinary regularity. The angular momentum was already there, inherited from the slowly rotating progenitor core. The compression amplified that rotation to tremendous speed. The density and rigidity stabilized it. The vacuum preserved it. The tilted magnetic field created a beam that broadcast the rotation to the cosmos. All of it, every piece, was a consequence of physics. Not of intention, not of design, not of purpose. Just physics, doing what physics inevitably does when a massive star runs out of fuel and its core collapses. The result is an object that seems almost paradoxical, born in chaos but supremely orderly, created by destruction but extraordinarily stable. Dead in the sense that nuclear fusion no longer powers it, but more regular in its behavior than the living star it came from ever was. The parent star was turbulent, variable, constantly churning with convection and flares and magnetic storms. The neutron star it left behind is steady, quiet, precise. A beacon in the darkness, ticking away with a regularity that the chaotic, burning, living star could never have achieved. This is why the collapse matters so much to our story. The collapse isn't just how the neutron star was created. The collapse is why the neutron star is a clock. Without the extreme compression, there would be no rapid spin. Without the extreme density, there would be no rotational stability. Without the extreme rigidity, there would be no clean rotation. Without the vacuum of space, there would be no preservation of that rotation over centuries and millennia. Every aspect of the pulsar's clock-like behavior traces back to the physics of the collapse. The collapse is the clockmaker, and the clock it makes is extraordinary. How extraordinary, how precise are we actually talking about? What does it mean to say a pulsar keeps time better than a star should? The answer involves numbers that will genuinely astonish you. Because the best pulsars don't just keep good time, they keep time so precisely that they are used as tools to detect the faintest ripples in space-time itself. And to understand that, we need to talk about a special category of pulsars, ones that spin not 30 times per second, but hundreds of times per second, with a stability that approaches, and sometimes rivals, the most precise clocks humanity has ever constructed. We've now seen that a neutron star can spin rapidly, and that its spin can be remarkably stable, a consequence of angular momentum conservation during collapse, extreme density, extraordinary rigidity, and the near-perfect vacuum of interstellar space. But now we need to get specific. We need to talk about numbers, because saying a pulsar is precise is one thing, Understanding just how precise it actually is changes the entire picture. And to appreciate the full scope of pulsar precision, we need to talk about a special breed of pulsar that takes everything we've discussed and pushes it to an almost absurd extreme. These are called millisecond pulsars, and they are among the most extraordinary timekeepers in the known universe. A normal pulsar, like the Crab pulsar, rotates somewhere between a few times per second and once every few seconds. These are already fast by any everyday standard, but millisecond pulsars rotate hundreds of times per second. The fastest known millisecond pulsar completes about 716 rotations every single second. 716 times per second. That means the entire neutron star, an object 20 kilometers across and weighing more than the Sun, is completing a full revolution in about 1.4 milliseconds. 1.4 thousandths of a second. In the time it takes you to blink, this object has rotated roughly 250 times. The equatorial surface of this neutron star is moving at roughly 15 to 20% of the speed of light. A solid surface made of material a billion times stiffer than steel, whipping around at 75,000 kilometers per second. The numbers are almost violent in their extremity. But here's what's truly remarkable. Millisecond pulsars don't just spin fast, they spin with extraordinary stability. Some of the best studied millisecond pulsars maintain their rotation rate to a precision of about 1 part in 10 to the 15th over timescales of years. Let me translate that into something concrete. 1 part in 10 to the 15th means that if you predicted when the next pulse would arrive based on your knowledge of the pulsar's rotation, and then you waited and measured when it actually arrived, your prediction would be accurate to within a few hundred nanoseconds over a span of several years. That's accurate to within a few hundred billionths of a second across years of observation. The pulsar ticks and ticks and ticks, and each tick arrives almost exactly when you predicted it would, to within a sliver of time so small that light itself travels less than 100 meters during the discrepancy. To put this in perspective, consider atomic clocks. The cesium atomic clocks that define the international standard of time are accurate to about 1 part in 10 to the 15 or 10 to the 16. They are the most precise timekeeping instruments humanity has ever built, the product of decades of engineering, careful environmental control, vacuum chambers, magnetic shielding, laser cooling of atoms, and sophisticated electronics. They sit in temperature-controlled laboratories in national standards institutes around the world, tended by teams of physicists. And the best millisecond pulsars approach this level of precision naturally. No engineering, no laboratory, no human involvement whatsoever. Just a dead star's core spinning in the vacuum of space, keeping time with a regularity that rivals the greatest achievements of human technology. This raises an obvious question. Where do millisecond pulsars come from? If a neutron star is born spinning a few times per second and gradually slows down due to magnetic dipole radiation, how do you end up with a neutron star spinning 700 times per second? The answer is that millisecond pulsars have been recycled. They've been given a second spin, a second life, through a remarkable process involving a companion star. Most millisecond pulsars are found in binary systems orbiting a companion star. The story goes something like this. A neutron star forms in a supernova explosion, just as we described. It starts out spinning relatively fast, maybe a few times per second. Over millions or billions of years, it gradually slows down as magnetic dipole radiation drains its rotational energy. Eventually, it slows to the point where its beam weakens and it becomes effectively invisible as a pulsar. It's still there, still a neutron star, but it's spinning too slowly and emitting too weakly to be detected. It becomes a dead pulsar, a quiet, dark neutron star drifting through space. But if the neutron star has a companion star, something remarkable can happen. As the companion evolves and expands, perhaps swelling into a red giant as it ages, material from the companion can be pulled onto the neutron star by its intense gravity. This material doesn't fall straight down. Because the companion is orbiting the neutron star, the infalling material carries angular momentum. It spirals in, forming a swirling disk of gas called an accretion disk around the neutron star. And as this material settles onto the neutron star's surface, it transfers its angular momentum to the star. Think of it like pushing a merry-go-round. Each push adds a little angular momentum, a little spin. The infalling material does the same thing. Each bit of accreted gas, spiraling in and landing on the neutron star's equator, gives the neutron star a tiny push in the direction of rotation. Over millions of years, the accumulated effect of all this accreted material spins the neutron star back up, faster and faster, until it's rotating hundreds of times per second. The dead pulsar is brought back to life, recycled, spun up to speeds even faster than when it was born. This process also has another important effect. It weakens the neutron star's magnetic field. The exact mechanism isn't fully understood, but observations clearly show that millisecond pulsars have magnetic fields roughly 1,000 to 10,000 times weaker than young pulsars. The Crab pulsar has a magnetic field of about 1 trillion Gauss. A typical millisecond pulsar has a magnetic field of about 100 million to 1 billion Gauss. Still enormously strong by everyday standards, hundreds of millions of times stronger than Earth's field, but weak by neutron star standards. And this weaker magnetic field is precisely why millisecond pulsars are more stable than ordinary pulsars. Remember, the main mechanism that slows a pulsar down is magnetic dipole radiation. The energy radiated away depends on the strength of the magnetic field. A stronger field means more radiation, which means faster slowdown. The Crab pulsar, with its powerful trillion Gauss field, slows down fast enough that the change is measurable within weeks. As we saw earlier, its period grows by tens of nanoseconds every day, a rate that accumulates visibly over months and years. That kind of drift would be ruinous for a precision clock. A millisecond pulsar, with its much weaker magnetic field, loses energy far more slowly. The slowdown rate might be a factor of 1,000,000 times smaller than the Crab pulsars. Some millisecond pulsars are slowing down so gradually that their periods change by less than 1 part in 10 to the 20th per second. The fractional change in their spin rate is so tiny it's almost undetectable. They're barely slowing down at all. And this means their rotation remains almost perfectly constant over human timescales, over decades and centuries of observation. There's another factor working in the millisecond pulsar's favor. Higher spin rate means more rotational energy, a lot more. Rotational energy scales with the square of the rotation rate. A pulsar spinning 600 times per second has vastly more rotational energy than one spinning twice per second. And because the energy stored in the spin is so enormous, any small perturbation, any little nudge or disturbance, represents a vanishingly tiny fraction of the total energy. It's like trying to slow down a freight train by blowing on it. The train has so much kinetic energy that your breath is utterly irrelevant. Similarly, a millisecond pulsar has so much rotational energy that small disturbances simply don't register in any meaningful way. The spin is overwhelmingly stable because the energy reservoir is overwhelmingly large, compared to anything that might perturb it. The combination of these factors, weak magnetic field producing minimal energy loss, enormous rotational energy rendering perturbations negligible, and all the structural advantages we discussed before, extreme density, rigidity, and vacuum, produces a timekeeping device of almost absurd precision. And astronomers have found ways to use this precision that go far beyond simply knowing what time it is. One of the most ambitious applications is called a pulsar timing array. The concept is deceptively simple. Take a collection of the most stable millisecond pulsars scattered across the sky. Monitor them continuously for years or decades. Measure the arrival time of every pulse with the best equipment you have. Build up a precise model of each pulsar's behavior, accounting for its rotation rate, its slowdown, its orbital motion if it's in a binary system, and the effects of Earth's motion through the solar system. Once you have this model, compare your predictions against the actual measured pulse arrival times. Any discrepancy, any deviation between when you predicted a pulse would arrive and when it actually did, tells you something is happening that your model didn't account for. Now, here's where it gets extraordinary. Gravitational waves, ripples in the fabric of space-time itself, would cause tiny changes in the distances between Earth and the pulsars. As a gravitational wave passes through the space between us and a distant pulsar, it stretches and compresses that space ever so slightly. This would cause the pulsar's signals to arrive a tiny bit earlier or later than expected. The effect is incredibly small. We're talking about timing changes of perhaps tens of nanoseconds, billionths of a second. But if you're monitoring a network of pulsars distributed across the sky, and a gravitational wave passes through, it should produce a specific correlated pattern in the timing deviations of all the pulsars in the array. Certain pairs of pulsars should show timing variations that are correlated in a specific mathematical way, depending on the angle between them on the sky. This predicted correlation pattern was worked out by Ronald Hellings and George Downes in 1983, and it serves as a unique fingerprint for gravitational waves. In 2023, multiple pulsar timing array collaborations around the world announced that they had found strong evidence for exactly this pattern. Nanograv, monitoring pulsars from North America, the EPTA in Europe, the PPTA in Australia, and the Combined International Effort, the IPTA. After monitoring dozens of millisecond pulsars for 15 or more years, they detected the telltale correlations. The signal is consistent with a background hum of gravitational waves, likely produced by pairs of supermassive black holes orbiting each other in the centers of merging galaxies throughout the universe. These are gravitational waves with periods of years to decades, far longer than the waves detected by ground-based detectors like LIGO, which detect waves with periods of milliseconds from colliding stellar mass black holes and neutron stars. Think about what this means. Astronomers used pulsars as a galaxy-scale gravitational wave detector. The pulsars served as the endpoints of a measuring instrument spanning thousands of light years. And the instrument worked because the pulsars are stable enough that deviations of a few tens of nanoseconds, accumulated over years, are meaningful and detectable above the noise. If the pulsars weren't this precise, the entire technique would be impossible. The timing deviations caused by gravitational waves would be lost in the random fluctuations of the pulsar signals. The fact that pulsar timing arrays work, the fact that they've actually detected gravitational waves, is itself one of the most powerful demonstrations of how extraordinarily stable millisecond pulsars are. And the precision doesn't stop at gravitational wave detection. Pulsar timing has been used to test general relativity in some of the most extreme environments accessible to observation. Binary pulsar systems, where a pulsar orbits another neutron star or a white dwarf, provide natural laboratories for testing Einstein's predictions. The orbital motion can be tracked with exquisite precision by measuring how the pulse arrival times change as the pulsar moves toward and away from Earth in its orbit. Astronomers have measured effects like the precession of the orbit, the slowing of time in a gravitational field, and the emission of gravitational waves from the orbiting pair. All of these measurements agree with general relativity to extraordinary accuracy. In some cases, the agreement is better than 1 part in a million. These tests are possible only because the pulsar's timing is precise enough to reveal the subtle effects that general relativity predicts. The most famous example of using pulsar precision to test general relativity is the Hulse-Taylor binary pulsar, discovered in 1974. Russell Hulse and Joseph Taylor, working at the Arecibo Observatory in Puerto Rico, discovered a pulsar designated PSRB 1913+16 that was behaving oddly. Its pulse period wasn't constant. It varied in a regular, periodic way, speeding up and slowing down over a cycle of about 7.75 hours. Hulse and Taylor realized what they were seeing. The pulsar was in a binary orbit with another neutron star. The two neutron stars were orbiting their common center of mass every 7.75 hours, and the varying pulse period was caused by the Doppler effect. When the pulsar was moving toward Earth in its orbit, the pulses arrived slightly more frequently. When it was moving away, they arrived slightly less frequently. The pattern of variation told them the orbital parameters with exquisite precision. What made this system so important was what happened next. Over the following years, Taylor and his colleagues monitored the system with extraordinary care, measuring the pulse arrival times to microsecond precision over many orbits. They noticed that the orbital period was decreasing. The two neutron stars were spiraling inward toward each other, their orbit shrinking by about 3.5 millimeters per orbit. This is a tiny change, but over years it accumulated to a measurable shift in the orbital timing. General relativity predicts exactly this behavior. Two massive objects orbiting each other should emit gravitational waves, ripples in space-time that carry energy away from the system. As the system loses energy to gravitational radiation, the orbit shrinks and the orbital period decreases. Einstein's equations predict precisely how quickly the orbit should shrink, given the masses and orbital parameters. Taylor and his colleagues compared the observed orbital decay to Einstein's prediction. The agreement was extraordinary. Over decades of observation, the measured orbital decay matched the prediction of general relativity to better than 1/3 of 1%. The two curves, prediction and observation, lay almost exactly on top of each other. This was the first indirect evidence for gravitational waves, confirming that gravitational radiation is real and carries energy away from orbiting masses exactly as Einstein predicted. Hulse and Taylor received the Nobel Prize in Physics in 1993 for this discovery. It remains one of the most precise confirmations of general relativity ever achieved, and it was made possible entirely by pulsar timing precision. Without the ability to measure pulse arrival times to microsecond accuracy over years, the tiny orbital decay would have been undetectable. The neutron star's clock-like regularity was the instrument that made the measurement possible. Now consider the accretion process that creates millisecond pulsars, because it's worth understanding in more physical detail. When a companion star overflows its Roche lobe, the gravitational boundary beyond which material is more attracted to the neutron star than to its parent star, gas streams toward the neutron star. But it doesn't fall straight in. The gas carries the orbital angular momentum of the companion star, so it spirals, forming a flattened disk of material swirling around the neutron star. This is the accretion disk. The gas in the disk orbits the neutron star at tremendous speed. Material in the inner disk, closest to the neutron star, orbits at a significant fraction of the speed of light. The gas is heated by friction and compression to temperatures of millions of degrees, causing it to glow brilliantly in X-rays. During the accretion phase, the system is visible as an X-ray binary, one of the brightest X-ray sources in the sky. The accretion continues for millions of years, sometimes hundreds of millions of years. Throughout this period, the neutron star is steadily gaining mass and angular momentum. Its spin rate climbs higher and higher. Its magnetic field, perhaps buried or reduced by the accreted material, weakens. When the companion star finally exhausts its envelope, when there's no more material left to transfer, the accretion stops. The X-ray emission fades, the disk dissipates, and what remains is a neutron star spinning hundreds of times per second with a weakened magnetic field. The radio emission mechanism reactivates, the lighthouse beam switches back on, and a millisecond pulsar is born. It has been recycled, brought back from the dead, spun up to extraordinary speeds by the patient, steady accumulation of angular momentum over geological timescales. Astronomers sometimes call these systems the black widows or redbacks of the pulsar world, because the neutron star has effectively consumed its companion to fuel its own resurrection. Pulsar timing has even been used to detect planets. In 1992, astronomer Alexander Volschan announced the discovery of 2 planets orbiting the millisecond pulsar PSRB 1257+12. These were the first confirmed planets ever found outside our solar system. The planets were detected through their gravitational influence on the pulsar. As the planets orbit, they tug the pulsar very slightly back and forth, changing its distance from Earth by tiny amounts. These distance changes show up as tiny periodic variations in pulse arrival times. The variations are small, corresponding to the pulsar moving back and forth by just a few million kilometers. But pulsar timing is precise enough to detect this. The discovery was confirmed, and a 3rd planet was later found in the same system. Exoplanet detection through pulsar timing predates the radial velocity method that later became the primary technique for finding planets around ordinary stars. Pulsars were the first tool humanity used to discover other worlds, because their precision made the detection possible before other techniques were mature enough. Now let's step back and contrast all of this with ordinary stars. Because the difference in regularity between a pulsar and a normal star is not just quantitative, it's almost qualitative. They're different kinds of objects behaving in fundamentally different ways. An ordinary star like our Sun is a roiling, churning, turbulent ball of plasma. Its surface is covered with convection cells, rising columns of hot gas that boil upward, cool, and sink back down. These cells are constantly shifting, forming and dissolving in patterns that change from minute to minute. The Sun has sunspots, dark regions where intense magnetic fields suppress convection. Sunspots come and go over an 11-year cycle, but the cycle itself is irregular. Some cycles produce many sunspots, others produce few. The exact timing and intensity of each cycle is unpredictable. Solar flares erupt without warning, releasing bursts of energy equivalent to billions of nuclear weapons. Coronal mass ejections hurl billions of tons of magnetized plasma into space at millions of kilometers per hour. The Sun's brightness varies by about 0.1% over the course of the 11-year sunspot cycle. That might sound tiny, but it's enormous compared to pulsar stability. The Sun's rotation is not even uniform. Different latitudes rotate at different speeds. The equator completes a rotation in about 25 days. The poles take about 35 days. This differential rotation shears the magnetic field, building up stress that eventually releases in violent flares and eruptions. Nothing about an ordinary star is precise. Stars are dynamic, variable, turbulent, and fundamentally unpredictable in their fine details. The very thing that makes a star alive, the nuclear fusion churning in its core, driving convection, generating magnetic fields, powering flares and winds, is the thing that makes it chaotic. A living star is a fundamentally messy object. It's constantly changing, constantly adjusting, constantly erupting and settling and erupting again. You could never use a star as a precision clock. The variations in its brightness, its spectrum, its magnetic activity are far too large and far too irregular. A pulsar is the opposite. It doesn't have convection because it's not powered by fusion. It doesn't have sunspots because its surface is a rigid, crystalline lattice, not a churning sea of plasma. It doesn't have flares, at least not in the way the Sun does. Its magnetic field is powerful but essentially frozen into the crust, not tangled and sheared by differential rotation. Everything that makes a star variable and unpredictable is absent from a pulsar. The pulsar is dead, in the sense that no ongoing energy generation drives its behavior. And paradoxically, that death is precisely what makes it so stable. The absence of an active energy source, the absence of convection and turbulence and magnetic dynamo activity, means the pulsar just sits there and spins, quietly, steadily, predictably. This contrast illuminates something deep about the nature of precision. Precision requires simplicity, or more precisely, precision requires the absence of uncontrolled disturbances. The most precise human clocks work by isolating a simple, repeatable physical process: the oscillation of a cesium atom, the vibration of a quartz crystal, from everything that might disturb it. Temperature variations, vibrations, electromagnetic interference, all of these degrade precision. The more thoroughly you isolate the oscillator, the more precise the clock becomes. A pulsar achieves this isolation naturally. Its oscillator, its rotation, is isolated by the vacuum of space, by the enormous energy stored in its spin, by the extraordinary rigidity of its structure, and by the weakness of its magnetic field in the case of millisecond pulsars. It's a clock that doesn't need a laboratory, because the universe itself provides the perfect laboratory conditions. There's something profoundly humbling about this. Humanity has spent centuries developing timekeeping technology, progressing from sundials to pendulums to quartz crystals to atomic clocks, each generation more precise than the last, each requiring more sophisticated engineering and more careful environmental control. And out in the darkness of interstellar space, scattered across the galaxy, nature has been producing clocks of comparable precision for billions of years. No engineering required, no careful control, just the inevitable consequence of a star dying, its core collapsing, and the resulting neutron star spinning in the void. Nature didn't set out to build a clock, but the physics of stellar collapse produces one anyway, and it produces a remarkably good one. Some millisecond pulsars have now been monitored continuously for decades. Astronomers have pulse arrival time records stretching back more than 30 years for some of the best studied objects. Over that span, the accumulated timing models are accurate to within microseconds. That means over 30 years of continuous rotation, hundreds of billions of individual rotations, the pulsar's behavior has been predictable to within millionths of a second. The pulsar did exactly what the physics said it would do, rotation after rotation after rotation, for decades, deviating by less than the time it takes light to travel a few hundred meters. This level of predictability is not just impressive, it's scientifically useful in ways that go beyond the specific applications we've discussed. Pulsar timing precision has been used to constrain the properties of nuclear matter at supranuclear densities. The exact rotation rate and the way it changes during rare glitches, those sudden tiny speed-ups caused by the superfluid interior abruptly transferring angular momentum to the crust, tell astronomers about the neutron star's internal structure. The size of each glitch, the rate of recovery afterward, and the frequency of glitches over time all constrain models of how matter behaves at nuclear density. Because the baseline rotation is so stable, even changes smaller than 1 part in a billion stand out clearly, giving physicists a direct probe into conditions no laboratory on Earth can reproduce. Pulsar timing has also been used to set limits on the existence of hypothetical objects and phenomena. If certain kinds of cosmic strings, theoretical defects in spacetime left over from the early universe, existed in abundance, they would produce gravitational wave signatures detectable by pulsar timing arrays. The fact that these signatures haven't been seen in the way certain models predict constrains those models. Pulsars serve as cosmic probes, their precision allowing astronomers to test ideas about the universe that have nothing directly to do with neutron stars themselves. There's a remarkable elegance to all of this. A dead star becomes a tool for understanding the living universe. An object that produces no light through fusion, that generates no new energy, that simply sits and spins in the darkness, becomes one of the most powerful observational instruments in all of astronomy. Not because anyone built it, not because anyone designed it, but because the laws of physics, applied to the simple situation of a collapsed stellar core rotating in a vacuum, inevitably produce something of extraordinary regularity. And that regularity, once recognized and measured, opens windows onto gravitational waves, general relativity, nuclear physics, and the large-scale structure of space-time. The journey from Bell-Burnell's scruff on a chart recorder to galaxy-scale gravitational wave detection with pulsar timing arrays is one of the great stories in the history of science. It begins with a graduate student noticing something odd in a stream of data. It continues with the identification of a new class of astrophysical object. It deepens with the discovery of millisecond pulsars and the realization that their precision rivals atomic clocks. And it culminates in the use of these natural clocks to detect ripples in the fabric of space-time itself, confirming a prediction Einstein made over a century ago and opening an entirely new way of observing the universe. All of it rests on one fact. A collapsed stellar core can spin with extraordinary stability. That single physical truth, rooted in angular momentum conservation, in the properties of matter at nuclear density, and in the simplicity of rotation in a vacuum, underpins everything. Without that stability, pulsars would be curiosities. With it, they are precision instruments, and the universe itself becomes a laboratory. But pulsars don't exist in isolation. They exist alongside other stellar remnants, other compact objects, other extreme products of stellar death. White dwarfs, magnetars, black holes. Each of these is related to the pulsar in some way, and each helps us understand why the pulsar occupies such a unique position. Because the pulsar isn't just any compact remnant, it's a specific kind of remnant, at a specific density, with a specific magnetic field strength, in a specific physical regime. And it's that specificity, that narrow window of physical conditions, that makes it the most precise natural clock the universe has to offer. Now that we understand what makes a pulsar such an extraordinary clock, a natural question arises. Why a pulsar specifically? The universe is filled with extreme objects. Stars die in various ways, leaving behind different kinds of remnants. If collapse and density and spin are the ingredients for precision, why don't other compact objects serve as natural clocks? The answer reveals that the pulsar occupies a very specific physical sweet spot, and understanding why that sweet spot exists and why other objects fall outside it completes the picture. Let's start with the white dwarf, because it's the most familiar compact remnant and the one that might seem, at first glance, like it should also work as a clock. A white dwarf is what remains when a star like our Sun dies, shedding its outer layers and leaving behind the exposed core. Roughly the size of Earth, but containing about half to slightly more than the mass of the Sun, a white dwarf is dense enough that a teaspoon of its material would weigh about 5 tons on Earth. And white dwarfs do rotate, some completing a revolution in minutes or even tens of seconds. So why can't a white dwarf serve as a precision clock the way a pulsar does? The fundamental problem is that a white dwarf is not dense enough and not compact enough. Remember, the precision of a pulsar's spin comes from the enormous rotational inertia created by extreme density, from the rigidity of its structure, and from the fact that the collapse amplified a slow rotation into a fast one. A white dwarf fails on all 3 counts compared to a neutron star. First, density. A white dwarf has a density of roughly 1 million grams per cubic centimetre. That's 1 million times denser than water. Impressive, certainly, but a neutron star is roughly 400 trillion grams per cubic centimetre. That's about 400 million times denser than a white dwarf. The neutron star's rotational inertia, its resistance to changes in spin, is correspondingly greater. A white dwarf stores far less energy in its rotation, and perturbations that would be utterly negligible for a neutron star can produce measurable effects on a white dwarf's spin. Second, compactness. A white dwarf is roughly the size of Earth, about 12,000 kilometers across. A neutron star is about 20 kilometers across. The white dwarf is 600 times larger. This means the same conservation of angular momentum that spins up a neutron star to thousands of rotations per second during collapse only spins up a white dwarf to relatively modest rotation rates. The progenitor core doesn't compress nearly as much when it becomes a white dwarf, so the amplification of rotation is far less dramatic. White dwarfs rotate with periods measured in seconds to hours. Neutron stars rotate with periods measured in milliseconds to seconds. The white dwarf simply cannot spin fast enough to serve as a precision clock on pulsar timescales. Third, there is a physical limit on how fast a white dwarf can spin. If you tried to spin a white dwarf at the rates we see in pulsars, it would tear itself apart. The centrifugal force at its equator would exceed the gravitational force holding it together. A white dwarf is held together by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain point. This pressure is strong enough to resist gravity at the white dwarf's relatively modest density, but it's not strong enough to resist the centrifugal forces that would result from spinning hundreds of times per second. There is a maximum rotation rate for a white dwarf, and it's far below pulsar spin rates. A white dwarf can't be a pulsar-class clock because it can't spin fast enough and remain intact. White dwarfs also lack the rigid crystalline crust that gives a neutron star its clean rotation. The interior of a white dwarf is a dense plasma of carbon and oxygen nuclei embedded in a sea of degenerate electrons. It can crystallize as it cools, forming a lattice structure, but this lattice is far less rigid than a neutron star's crust. And even if a white dwarf did have some mechanism for producing a beam of radiation, which most don't in the way pulsars do, its rotation would be too slow and too susceptible to perturbation to serve as a precision timekeeper. The white dwarf is too large, too loosely structured, and too slowly spinning to occupy the pulsar's niche. Now consider the opposite extreme. Not an object that is less dense than a neutron star, but one that is in some sense too extreme, the magnetar. A magnetar is a neutron star. It has the same basic structure, roughly the same size, roughly the same mass, roughly the same density. It was born in the same way, through the core collapse of a massive star. In terms of its fundamental physical properties, a magnetar is almost identical to a pulsar. But there is one critical difference: its magnetic field. A typical pulsar has a magnetic field of about 1 trillion Gauss. A magnetar has a magnetic field of about 1 quadrillion Gauss, or more. That's roughly 1,000 times stronger than an ordinary pulsar's field. And this difference changes everything about the magnetar's behavior. The magnetic field of a magnetar is so powerful that it dominates the object's physics in ways that a pulsar's field does not. The field stores enormous amounts of energy, and that energy is not stored quietly. The magnetic field lines threading through the neutron star's crust are under immense tension. As the magnetar rotates and its interior evolves, stresses build up in the crust, and periodically the crust fractures. It cracks, suddenly and violently, in events called starquakes. When the crust cracks, the magnetic field reconfigures, releasing a tremendous burst of energy in the form of gamma rays and X-rays. These are called magnetar flares, and they can be spectacularly powerful. On December 27, 2004, a magnetar designated SGR 1806-20, located about 50,000 light-years from Earth on the far side of the Milky Way, produced a giant flare so powerful that it briefly affected Earth's ionosphere. From 50,000 light-years away, a burst of radiation from a neutron star halfway across the galaxy was intense enough to measurably alter the electrical properties of Earth's upper atmosphere. In the fraction of a second that the initial spike lasted, this magnetar released more energy than the Sun emits in 250,000 years. It was one of the most powerful events ever observed from within our galaxy, and it came not from a supernova or a black hole, but from the cracking crust of a neutron star with an extraordinarily powerful magnetic field. This is the key distinction. A pulsar is stable. A magnetar is violently unstable. A pulsar's relatively modest magnetic field produces a steady beam and a gradual, predictable slowdown. A magnetar's titanic magnetic field produces sudden, unpredictable bursts of energy, starquakes that wrench the crust and alter the spin, and erratic behavior that makes precision timekeeping impossible. Magnetars do rotate, and they do emit periodic signals in some cases, but their rotation is disrupted by frequent glitches, sudden changes in spin rate caused by starquakes, and internal restructuring. Their pulse profiles are variable, their emission is erratic, they're anti-clocks, if anything. They're neutron stars where the magnetic field has become so dominant that it overwhelms the very stability that makes pulsars useful as timekeepers. In 2020, a magnetar called SGR 1935 + 2154 did something remarkable. It produced a burst of radio waves that was briefly as bright as the radio emission from some pulsars. For a fleeting moment, this magnetar looked like a pulsar, but only for a moment. Its emission was transient, erratic, and associated with a burst of X-rays from a magnetar flare. It was not the steady, repeating, predictable pulse of a true pulsar. It was a scream, not a tick. The magnetar's radio emission underscored the difference. Pulsars tick. Magnetars erupt. The contrast between a pulsar and a magnetar is one of the most instructive comparisons in all of astrophysics. They are the same type of object, a neutron star, with the same density, the same basic size, the same basic composition. The only major difference is the strength of the magnetic field. And yet, that one difference transforms the object from one of the most precise natural clocks in the universe into one of the most violently unpredictable sources of energy in the galaxy. It tells you that the pulsar's precision is not just about being a neutron star. It's about being a neutron star with the right magnetic field, strong enough to produce a coherent beam of radiation, but not so strong that it tears the crust apart and disrupts the spin. The pulsar lives in a Goldilocks zone of magnetic field strength, and the magnetar falls outside it. Now let's consider the black hole. A black hole is what you get when a stellar core is too massive to be supported even by the pressure of neutrons packed at nuclear density. If the collapsing core exceeds about 2 to 2.5 solar masses, nothing can stop the collapse. The material keeps falling inward, past the density of a neutron star, past every threshold known to physics, until it forms a singularity, a point of theoretically infinite density, surrounded by an event horizon, a boundary beyond which nothing, not even light, can escape. Black holes can spin. In fact, most astrophysical black holes are thought to spin, some very rapidly. A spinning black hole drags space-time around with it in an effect called frame dragging, predicted by general relativity. And some black holes are surrounded by accretion disks of gas spiraling inward, emitting enormous amounts of radiation as the gas heats up from friction and compression. Black holes are powerful, dynamic objects. They are among the most energetic phenomena in the universe. But a black hole cannot be a pulsar. The reason is fundamental. A black hole has no surface. A pulsar produces its beam because charged particles are accelerated along magnetic field lines anchored to the neutron star's solid crust. The magnetic field rotates with the crust, and the beam rotates with the magnetic field. The whole mechanism depends on a solid, magnetized surface. A black hole has no such surface. It has an event horizon, which is not a physical surface, but a mathematical boundary. Material can cross it, but nothing sits on it. You cannot anchor a magnetic field to an event horizon the way you can anchor one to a neutron star's crust. Without a surface, there's no mechanism to produce the kind of narrow, stable, rotating beam that defines a pulsar. Black holes can produce jets, powerful, collimated outflows of matter and energy that can extend for thousands of light years. These jets are produced by the interaction of the accretion disk's magnetic field with the spinning black hole's spacetime. They're impressive, but they're not pulsar-like beams. They don't produce the kind of regular, periodic, clock-like signal that a pulsar does. Jets are broad, variable, and driven by the complex dynamics of accretion, not by the clean rotation of a solid body. A black hole might be more extreme than a neutron star in terms of gravity and density, but that very extremity, the absence of a surface, the absence of a crust, the absence of an anchored magnetic field, prevents it from being a clock. There is also no way to observe a black hole's rotation directly through periodic pulses. The black hole spins, but it doesn't broadcast that spin the way a pulsar does. It has no lighthouse beam. The frame dragging effect is real and measurable through its influence on orbiting matter and light, but it doesn't produce a periodic signal in the radio spectrum that an observer could time with nanosecond precision. The black hole's rotation is hidden behind the event horizon, detectable only indirectly. It's a spinning object that gives you no ticks to count. And then there are ordinary stars. We touched on this earlier, but it's worth restating in the context of this comparison. Ordinary stars are too large, too fluid, too turbulent, and too variable to serve as precision clocks. The Sun rotates once roughly every 25 days at the equator and about 35 days near the poles. This differential rotation immediately tells you the Sun is not a rigid body. It's a ball of plasma, and different parts of it rotate at different rates. The magnetic field is tangled and sheared by this differential rotation, building up stress that releases in flares and coronal mass ejections. The brightness varies, the surface churns, sunspots come and go. Everything about an ordinary star is dynamic and variable. Even the most regular variable stars, like Cepheids, which pulsate with impressively regular periods, used as distance indicators in astronomy, are nowhere near as precise as pulsars. Cepheid periods are regular enough to be useful for measuring cosmic distances, but their precision is many orders of magnitude worse than that of a millisecond pulsar. A Cepheid might maintain its period to within a few parts per million. A millisecond pulsar maintains its period to within a few parts in 10 to the 15th. The comparison isn't even close. So the pulsar occupies a unique position. It is denser than a white dwarf, but not collapsed into a black hole. It is magnetized enough to produce a coherent radiation beam, but not so magnetized that it becomes a violently unstable magnetar. It has a solid surface that anchors its magnetic field, unlike a black hole. It's compact enough that the collapse of its progenitor core amplified its rotation to extreme speeds, unlike a white dwarf. It's dead, in the sense that no fusion or accretion currently drives its behavior, unlike an ordinary star whose ongoing energy production creates turbulence and variability. Every attribute of the pulsar conspires to make it a clock. Remove any one attribute, make it less dense, make it more magnetic, take away its surface, give it an active energy source, and the precision disappears. This is not a coincidence, it's physics. The pulsar doesn't occupy this sweet spot by accident or by design. It occupies it because the laws of physics, applied to a particular range of progenitor masses and magnetic field strengths and evolutionary histories, inevitably produce an object with these properties. Stars within a certain mass range produce neutron stars when they die. Neutron stars within a certain range of magnetic field strengths become stable pulsars rather than erratic magnetars. Neutron stars that accrete material from companion stars get spun up into millisecond pulsars with weakened magnetic fields. At each step, the physics determines the outcome, and the outcome, for a specific subset of neutron stars, is a natural clock of extraordinary precision. There's something almost philosophical about this. We tend to associate clocks with intention. A clock is something that is built, designed, calibrated. It's an artifact of intelligence. The idea that nature produces clocks, objects that keep time with a precision rivaling the best human technology, seems almost paradoxical, but it makes perfect sense once you understand the physics. A clock is just a system that repeats a simple process with minimal disruption. A pulsar repeats a simple process, rotation, with minimal disruption, because its density stabilizes it, its rigidity prevents internal dissipation, the vacuum eliminates drag, and its magnetic field is just strong enough to produce a signal, but not strong enough to cause instability. The pulsar doesn't know it's a clock. It doesn't intend to be a clock. It simply is one, because the physics demands it. And what a clock it is. Millisecond pulsars have now been observed for decades. Some have been timed continuously for more than 30 years. Over that span, billions of individual rotations have been predicted and measured, each pulse arriving within microseconds of its predicted time. These objects have been used to detect gravitational waves, test general relativity, discover the first exoplanets, constrain the equation of state of nuclear matter at extreme densities, and set limits on hypothetical objects and forces. They've provided evidence for phenomena that no other instrument could detect. They've opened windows onto physics that no laboratory on Earth can access. All because a dead star spins steadily in the dark. When Jocelyn Bell Burnell noticed that quarter-inch of scruff on her chart paper in 1967, she had no idea she was looking at one of the most precise natural phenomena in the universe. She didn't know that the strange repeating signal was the heartbeat of a collapsed star. She didn't know that decades later, astronomers would use similar objects as the endpoints of a galaxy-spanning gravitational wave detector. She didn't know that the little blips on her chart recorder would lead to Nobel Prizes, to the discovery of new planets, to tests of Einstein's general relativity in the most extreme environments imaginable. She just noticed something odd, and she had the scientific instinct and the intellectual discipline to follow it up rather than dismiss it. The story of pulsars is a story about what happens when destruction produces order. When a massive star dies, when its core collapses in a fraction of a second under forces beyond imagination, when matter is crushed to densities that exist nowhere else in the observable universe, the result is not chaos. The result is one of the most orderly objects nature has ever produced. A spinning remnant of extraordinary regularity, broadcasting its rotation to the cosmos with metronomic precision, keeping time better than any star has a right to. It's tempting to say there's a lesson in this, and perhaps there is. The universe doesn't care about our intuitions. We expect destruction to produce disorder. We expect death to produce silence. We expect collapse to produce chaos. And most of the time, we're right. But sometimes, under the right conditions, with the right physics, destruction produces something unexpected, something precise, something useful, something beautiful in its regularity. The pulsar is a reminder that the laws of physics can produce order from the most violent events imaginable, not because anyone intended it, but because the mathematics demands it. Conservation of angular momentum doesn't stop working just because a star is dying. Density doesn't stop conferring stability just because the circumstances of its creation were catastrophic. The vacuum of space doesn't stop preserving rotation just because the object spinning within it was born in an explosion that briefly outshone a galaxy. The pulsar is not a designed clock. It is an emergent one. It arises from the intersection of a handful of physical principles, each of them simple, each of them well understood, each of them applying to countless other situations throughout the universe. Angular momentum is conserved. Dense objects resist changes in rotation. Rigid bodies spin cleanly. Vacuum preserves spin. Tilted magnetic fields produce beams. None of these principles is exotic or surprising on its own, but when you apply all of them simultaneously to the specific case of a collapsed stellar core, a neutron star born from a supernova spinning in interstellar space, you get a clock. Not an approximate clock, not a rough timekeeper, a precision instrument, stable to 1 part in 10 to the 15th, capable of detecting ripples in the fabric of space-time from the mergers of supermassive black holes billions of light-years away. All from a dead star spinning in the dark. That is why a pulsar can keep time better than a star should. Not because it was built to, not because some special mechanism was installed, but because the physics of stellar collapse, of nuclear density matter, of angular momentum conservation, of electromagnetic radiation from a tilted magnetic field, inevitably produces an object of extraordinary regularity. The precision is not surprising once you understand the physics. It's inevitable. It's what happens when you crush a stellar core to the density of an atomic nucleus and let it spin. The universe doesn't need a clockmaker. The laws of physics are the clockmaker, and the clock they make is among the finest the cosmos has ever produced. The next time you look up at the night sky and see the faint glow of the Milky Way stretching overhead, remember that scattered throughout that river of light are thousands of pulsars. Dead stars, spinning in silence, keeping time with a regularity that took humanity centuries of technological development to match. They've been ticking since before our species existed. Some of them have been ticking since before the Earth itself formed. They'll keep ticking long after we're gone, long after the sun swells into a red giant and swallows the inner planets, long after the solar system dissolves into the slow drift of the galaxy. They are among the most patient, most reliable, most enduring objects the universe has ever created. And they were made not by intention, not by design, but by the simple, relentless, inevitable workings of physics applied to the death of a star. Thank you for joining me on this journey tonight. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep dives into the science of the cosmos. And the next time someone tells you that nothing good comes from destruction, you can tell them about pulsars, about how the most violent event a star can experience produces one of the most precise objects in the known universe, about how death creates a clock that ticks for billions of years, about how the universe, without trying, without intending, builds timepieces that rival the best our civilization has ever constructed. Good night, and may you never look at the stars the same way again.